So the purpose in introducing the block function was less about doing any rigorous math to compute what the actual wave functions were, which is something that would be reserved for a more advanced class, but more to relate to the origins of this really important diagram called the band structure diagram. And before this, we've referred to our sort of rectangles that represented the amount of charge carriers in a band as band diagrams. There's a variety of band diagrams, but I would say what we've represented before is one model that's ultra simplistic. And now we're also representing a band diagram, but with more nuance and a little bit more detail. And these band structure diagrams are the ones that you would find published either in textbooks or in papers that give you information about the overall electronic or band structure of a solid. And so they're called band structure diagrams. People call them band diagrams for short, and sometimes you'll see them referred to as EK diagrams. And the reason for that is because they're plots of energy of the crystal orbitals, which remember, crystal orbitals are essentially molecular orbitals for all of the atoms in the lattice points over the infinite crystal. And that energy of the orbitals is plotted as a function of k. And just a review of the block function here, this is the block function, which is representing psi. That's the wave function in 3 dimensions as a function of the wave vector k here. And the important takeaway was that it was periodic. That was the point of the block function, is that it reduces to this sine function that represents the periodicity of the lattice, so that every period 2 pi or 2 pi radians, we get exactly the same wave function. And that's a requirement of any sort of description of the electronic structure of a crystalline material, because you can't have a different wave function at every different lattice point. That wouldn't make sense, because these atoms don't know any different, and if you were to zoom in and start moving around these atoms, the electronic structure wouldn't be any different. They don't behave any differently. And so that's what's unique about the block function. And we talked about a couple different solutions, which are maybe the boundaries of possible values of k. And because this is sinusoidal, then really k can exist over some range of 2 pi. And because it's symmetric over that range of 2 pi, then if k is like right in the middle of that, then it really can go out to pi and negative pi. And in between that, those are the possible values for k. And so we solve for k at 0, which would be right in the center, and then out at its positive extreme, which would be pi over a. And we related that back to what our intuitive definition for molecular orbitals would have been, which would have been, and these are flipped by the way that I described them before, but we essentially get the fully symmetric bonding set, which is the sigma. That's our bonding orbital of the band. That's the bottom of the band. And then we get the fully antisymmetric, where we have alternating phases of our 1s orbitals. Again, these are the linear change of hydrogen 1s atoms, and that represents the antibonding of the top band. So that was the summary of the block function. And now we can think about then the consequence of this in terms of how we can relate the energy as a function of k. We couldn't go straight to band structure without introducing k as essentially a quantum number for a crystal, because it wouldn't make any sense unless you've thought about it, at least at this level of complexity. So I switched around our picture over here just to make it more cogent with the picture we're about to draw. So here we have the antibonding. That's the higher energy set. That would be higher in energy if I have an energy scale here, and the fully symmetric bonding set. So that's our sigma bonding part of the band. And so here's our EK diagram, and there's nothing plotted yet because we're going to build it up. So we have our energy as a function of k, our quantum number, our wave vector k, and we know that it can take the range k to pi over a, and if it's symmetric, then we only really need to represent the values of k in between there. So here's 0, here's pi over a, and then after this point, this picture would repeat. So if we're thinking about maybe the extreme example, which would be just a couple hydrogen 1s atoms here, and that we wouldn't really need this for that because we have the molecular orbital theory, but the theory is essentially the same. This is just a mathematical representation of that. Then in that case, we would have really just 2 discrete states to represent. We would have this at 0, and that would be the energy of this and let's just say this is for only two. So we would only, if we had two atomic orbitals going in, we'd have two molecular orbitals. So here's our first molecular orbital, and then we'd have the antibonding one, which would be maybe somewhere up here, right? And we'd know that we have, as we increased and we added a third, then we'd probably have some state in between there. If we add a fourth, etc., up through n, as you keep adding more states, the same analogy that we use to develop the band is operative here, where these become no longer discrete. Instead, they become a continuum because the actual delta energy between any one of them is so small, because we have Avogadro's number, essentially, per cubic centimeter of most materials. So for our infinite linear chain of hydrogen 1s orbitals, we'd get a band diagram that looks something like this, where we, at the k of 0, we get the fully bonding set, and that's the sigma bottom of the band, and that is at the lowest energy. And then we have a continuum each. So you imagine if you were to zoom in infinitely, these would be individual horizontal lines representing every possible state, because we would have a unique state for every single atom that we have, right? That would be the consequence of this. And so without zooming in, it looks like a continuum that spans from the low to the high anti-bonding state. So hopefully this is maybe a different representation, and it's invoking the use of this quantum number k, but intuitively the outcome is still largely the same as what you might have thought, right? That we have some spread in energies from the lowest bonding orbital state to the highest anti-bonding orbital state, where we have the maximum number of nodal planes separating the phases of those combined orbital states. And since we only have the single type of atom and the single type of orbital that are being combined here, we only have one band. And so as we increase the number or the difference in atoms, we have a heterogeneous sample in our unit cell, then we start to have more bands. But right here, this is the simplest representation of a homogeneous, simplest possible atom that we could think about. So we've got a single band. So to maybe put that more plainly, the number of bands that we would see in our band diagram, which accounts for these continuous lines, that's equal to the number of distinct atomic orbitals that are in the unit cell. And since we only had the 1s orbitals here, we only have a single band here. If we had something more complex that had p orbitals or d orbitals, we would have a band produced for each one of those original atomic orbitals. Another consequence of this sort of simple model is that the bands run uphill. So we often, you'll see this in books and papers, is that the bands are running, and that's another way of expressing from this sort of highly symmetrical low energy k point at k0 to the highly unsymmetrical or asymmetrical pi over a. It's running in this uphill format, which is to say we're going increasing in energy from the fully bonding to the fully anti-bonding state. And we can label that run, that delta there, the energy span between the top and the bottom of that band, is the band width, which I have labeled in blue here, which as a quantity we often call W for width. So that's the band width, which is really the span of energy between the fully bonding and the fully anti-bonding state, which in the EK diagram is the difference between the lowest energy of a particular band to the highest part of a particular band. So let's think about what properties of a crystal give rise to differences in bandwidth. So bandwidth, again, is this W, represented as W, and it's the energy distance, or the difference in energy, between when k is 0 and k is pi over a. And so it's represented here as W. And we can think about that as the energy difference, essentially, between the fully bonding, like 0 nodal plane representation of the crystal orbitals, and the fully anti-bonding, like the highest number of nodal planes in that crystal orbital. That's the span. And if we think about like what dictates that span, well, we know as chemists how to think about that, right? The strength of the bond, which is really a function of the overlap. So if you have a greater overlap in space of these orbitals, then that's going to lower this energy. And consequently, if you have a lot of overlap of opposed phases, then that's going to really destabilize this one, this version. And so the difference between those, which is the band gap, or not the band gap, sorry, the bandwidth in this case, is going to be higher. And so I've sort of given you drawings of EK diagrams or band structure diagrams for two scenarios of the same one-dimensional hydrogen crystal. So here I've got the lattice parameter of an angstrom, which I'm representing here with the atoms being pretty closely spaced together, and then doubling that, so to 2 angstroms. So it's the same linear chain, I'm just doubling the distance. Well, intuitively, you would think that as I increase the distance between the atoms, then they have less overlap, which means a weaker bond, and that's exactly what we see in terms of the outcome of our EK diagram. So when we have really closely spaced atoms, we have a higher overlap integral. Literally, if you integrated the space that these spheres are overlapping in space, they're 1s orbitals, that's representative of the bond strength, and so that's a really low energy. And because they're so close to each other, then when you overlap antiphase orbitals or opposite phase orbitals like this, then it's really destabilizing. That's not good. So we get a really, really large bandwidth, which in the case if we actually did this math out, this would be like 40 electron volts, which is sort of an incredibly high number, right? When we're thinking about like band gaps in silicon, for example, are like 1 eV. But if we put these super duper close to each other, then we end up with a huge spread. And if we double this up, we get them further away from each other, then that means a weaker bond, less overlap down here, so maybe that's whatever our bonding energy is. But then we don't get the penalty when we overlap these opposing phase, right? If only a fraction, a small fraction of these two orbitals are overlapping in space, then it's not as destabilizing. And so weaker bonds, weaker interactions between atoms mean a smaller bandwidth in our energy diagram. By the way, if we do the math for the EK diagram, assuming 2 angstroms, then our band gap goes down by about an order of magnitude. And so the bandwidth, I keep saying band gap, bandwidth goes down from about 40 eV in the 1 angstrom case to about 4 in the 2 angstrom case. So what does this difference in bandwidth mean for the physical representation of these electrons? Well, if we have a larger or a wider bandwidth, like we do in the case where we have maximum overlap, we've got about an angstrom difference in the lattice parameter, that means that the electrons can be more delocalized over the crystal lattice. So there's a much wider distribution of where that electron resides, and that as a consequence means that the electrons are more mobile, right? They're not relegated physically in space to 1 or 2 atoms. They're distributed widely, just like we think about conjugation in conjugated molecules, right? Those are typically more conductive, more stable. And in this case, that gives higher mobility, which is mu, as we introduced before, and we know that mu is directly related to conductivity, sigma, and so we typically see a higher conductivity in materials that have these wider bandwidths. So the opposite of that is if we have a narrow bandwidth structure, then we have electrons that are much more localized, and in some cases they can be constrained to individual atoms or even or spread out a little bit, but not over the whole crystal, and so just around clusters of atoms. So that constrains the mobility because you're pinning those electrons into physical points inside the crystal, so they can't move around as much, which typically means that there's a decreasing trend in the conductivity